This video is about the tools and materials you will need to build the Steering Pad 900F. Keep in mind that I didn't design this project around fancy tools I have access to. The goal was to make something accessible to any maker, especially beginners. While some skills are needed, you can build it using simple and inexpensive tools. Starting with the tools, a 3D printer is not strictly necessary. You can use online 3D printing services to get your parts. For the electronics, a soldering iron is mandatory. Any basic model will do. I also recommend having some soldering paste to help clean the contact points and, of course, a soldering wire. If you are not very experienced with soldering, it's a good idea to get some desoldering copper mesh to help removing excess solder. Still, on the electronics side, I also suggest having tweezers, a cutting pliers, I actually use a nail clipper, an X-Acto knife, a 3mm drill and a hold toothbrush to clean the board with acetone or alcohol. Another useful accessory is a helping hand tool with alligator clips. You will also need a crimping tool to attach connectors to the wires. This is essential for making secure and reliable connections, but it is possible to clamp them using a regular pliers. If you are a beginner, get a real one. Sanding some parts will be necessary. I use a small nail sander, a sanding sponge, or a flat board with sandpaper glued on top. Mine actually has 3 different grit levels. This is the best solution for flat, straight sanding. And if you are making your own, use a water-resistant board so you can wash it, or even sand under running water, which helps the sandpaper last much longer. This one here is 12 years old and still going strong. By the way, this base is made from phenolic board, which is water-resistant. To avoid damaging your dining table, use a scrapped MDF board as a work surface for cutting and sanding. I also place one piece of the cheapest camping sleeping mat I could find underneath, just a thin, dense foam. It's great to prevent scratches and adds grip to the board. To assemble the 3D printed parts and mount all sections together, I use Phillips 1 and Phillips 2 screwdrivers and a 7mm X-nut driver. One of the printed parts even includes a compatible tool for this. The steering wheel spiral will require some press fitting. You can hammer the locking pins into place, but using a press is preferable. A regular vise just works fine. The same goes for the swing arm bearing. The main components are the Pro Micro Development Board, the Pololu driver, the 16-bit ADC module, and the display. There are several different versions of the Pro Micro board, but from all the ones I tested, only one could handle the power drain from the force feedback motor. The version I'm using is the USB-C model, but the important detail is on the back of the board, where you will see a few extra components. I believe these 2 capacitors are the key to properly filtering the noise generated by the motor and keeping the circuit stable and responsive. I also found a very cheap version of this board, which seems to be a low-quality clone. It was very inexpensive, and the silk screen printing was slightly blurry. This one actually performed better than the versions without the backside components, but still wasn't able to keep the signal clean when the motor was spinning. That said, all of them work fine if you disable force feedback. So, be careful, buy the version with the extra components on the back, and ideally the one with clean printing and reliable quality. In short, the more expensive one. The Pololu DRV8838 is the motor driver used in this project. It's an older model, but it works perfectly. It's also the most expensive electronic component in the build, and it's hard to find a reliable chip clone, so I recommend buying an original one. For the analog inputs, I'm using the ADS1115 analog to digital converter. This chip has 4 16-bit resolution channels and communicates with the Pro Micro using the I2C protocol. In this project, I'm using 3 channels, 1 for steering and 2 for the pedals, leaving the 4th channel unused. So, adding an analog clutch pedal in the future wouldn't require changing any of the electronics. The last pre-built component is the display. I'm using a very cheap OLED screen with 128 by 64 pixel resolution. These displays come into 3 different color options, and they also use I2C for communication. The position of the steering wheel and pedals is read by Hall sensors, the 49E model. You will need at least 3 of them, 1 for each analog axis. These sensors detect variations in the magnetic field around them, and to create that variation, I'm using neodymium round magnets, sized 10mm by 4mm. You will need at least 5 magnets, including one for the steering wheel face. If you are planning to design and print your own custom steering faces, you will need 1 extra magnet per face. For the buttons, I'm using these 12 by 6 by 6mm micro switches with a straight short lever. You will need 13 of them. I also had a tactile button under the display. Its function is to reset the Pro Micro. Sometimes the microcontroller freezes, especially when you are trying new features in the code and you have bugs. And the only way to upload working code again is to press the reset while uploading. You won't need this button if you are just uploading the firmware I provide. However, if you are planning on tweaking or experiment with the code, it's a good idea to add it. It's up to you. And yes, it's always possible to reset the board manually without the button. You will have to open the box and short the reset pin to the ground using a wire or tool. Even though I have 11 buttons on the top board and just 4 inputs available, I had to use a few tricks to make all the buttons work independently with just 4 wires. All buttons are connected to the board using resistors. For the entire build, you will need 4 10K resistors, 4 20K resistors, 4 33K resistors, 3 100K resistors, 1 100 nanofarad and 1 100 microfarads capacitor. This one is 50 volts. To connect all the components and have a PCB board, I'm using a line-by-line prototype BREF board. This type of board has horizontal copper lines running along the long side. It features 36 lines with 50 holes each. I like using this type of board because I don't need to create the tracks with solder, and the final result looks much cleaner. On the downside, when designing with these boards, I have to take into account the built-in horizontal connections on the backside. Let me know in the comments if you want a dedicated video explaining how I design with these boards. One board should be enough to build the whole controller, as long as you don't mess up the cuts. The other side of the board is where the components go, and also where I make the vertical connections between the components and the horizontal tracks. To make these connections, I use 24 gauge or around 0.5mm solid core wire. It's easy to bend and keeps its shape. To connect both boards, you will need female connectors on the bottom board and male pins on the top one. The female headers are these 12-pin sockets with short legs. For the top board, I'm using a strip of male pins. You can find these in longer strips, but they are easy to cut to size. The Pro Micro should already have its own pins. In total, you need 4 12-pin strips to attach the Pro Micro and connect both boards. To connect the sensors, the turning signal buttons and the motor, I'm using L-shaped header pins. The cables need to exit horizontally to avoid interfering with other components, so make sure you get the pre-bent L-shaped pins. Don't try to bend the straight ones. You will need at least one 19-pin strip of this. On the cable side, you need DuPont type connectors, a 3-pin housing for the turning signal, a 2-pin housing for the motor, and a 4-pin housing for the sensors. Inside, you need a female connector, in a total of 14. The 4-pin housing only takes 3 connectors inside, arranged in a way to prevent burning the sensor if are connected in the wrong direction. The final electronic component is the motor. I'm using a 1.5 to 6 volt DC motor. It has a 24.3 mm diameter, a height of 12.4 mm and a shaft that is 6.2 mm long. All parts were designed to be assembled using screws. Here is the list of what you will need: 13 conical M4 10 mm screws, 17 M3 5 mm screws, 6 M3 10 mm screws, 5 M3 16 mm screws, 1 M4 10 mm screw, and 2 external hexagonal M4 with 30 mm. If you can get a 32 mm one for the pedals, it's even better, but the 30 mm version works fine. Some screws go directly into the plastic, but others require more strength and need a nut. Here is the list of nuts: 9 M4 nuts, 2 M4 locking nuts, 3 M3 nuts. Some of the parts rotate and you will need washers to reduce friction. The washer list is 5 M3 by 7 by 0.5 mm washers and 6 M4 by 9 by 0.5 mm washers. Certain mechanisms need springs to function properly, like the pedals returning to the top or the key rotating back by itself. You will need 6 springs in 3 different types. 1 30 mm by 3 mm with a 0.3 mm wire. 3 25 mm by 3 mm with a 0.4 mm wire. And 2 30 mm by 5 mm with a 0.5 mm wire. Note that all springs' length include the loop that wraps around the screw. To transfer the movement from the motor to the steering mechanism, you will need a belt of 80 mm with 2.5 mm diameter. Finally, the bearings. The smoothness of the steering wheel mechanism depends on 3 bearings: 2 F8 22M thrust bearings used on the steering wheel axis, and 1 4 by 13 by 5 mm 624 ZZ bearing used on the swing arm. The swing arm will rock the spiral using a metal pin. I'm using a brass rod with a 3 mm diameter and approximately 15 mm in length, which I cut from a longer piece. To ensure this interaction happens smoothly and with minimal friction, a bit of lubricant is recommended. Oil tends to drip out, so I suggest using synthetic grease for plastic gears instead. The cost of these components will vary depending on how you buy them and also the shipping costs to your location. I got my components from AliExpress, Amazon and eBay. In some cases, I couldn't find the components in the single pack, so I had to buy more than the ones I needed. This means the cost will be greater than the unity cost of a single controller. As you can see in the spreadsheet, I spent around 166 euros without shipping cost and tools, but the controller only needs 46 euros worth of materials. In reality, I have components to make more than one controller, so in your case, your controller may actually be free. You just have to trade your assembly skills with your friends if they want one. This is all you need to make your own Steering Pad 900F. I strongly believe I didn't forget anything. Check the description for any correction. I hope this video encourages you and helps clarify what you will need to get started. If you have any questions, feel free to drop them in the comments with timestamps if possible. I will be happy to help. Don't forget, you will find a link to the full material spreadsheet in the video description and a PDF copy in my project page. In the next video, I will talk about the 3D printing process with tips to ensure your parts come out precise and functional. And for now, thank you for watching, like and subscribe, and I hope to have you in the next video.